What I'm going to do is show you, it's sort of a simple version of what's called the likelihood ratio test. And here we're basically assuming that the cost of calling a skin pixel not skin is the same as cost calling a not skin pixel skin. We can reweight these things if the costs are different. Likelihood ratio test says basically, look, it's just exactly what you think. If the probability that it's skin given the hue measurement is greater than the probability that it's not skin, what am I going to do? I'm going to call it skin. Right? That assumes that the costs are equal. So using Bayes' rule, P of skin given x is just P of x given skin times P of skin. P of not skin given x is P of x given not skin times P of not skin. So if this quantity is greater than this whole quantity, we're going to classify x as skin. This is just a direct use of Bayes' rule. And as I said before, we would change the weights on two sides of that equation if the costs of making the mistakes were not symmetric, all right? So problem is I don't really know the prior of being skin, right? I mean, I don't know where's the prior? So the one thing I'm going to do is I'm going to assume it's a constant. I'm going to assume it has some number, right? So the prior for a whole bunch of pixels that I'm looking at that are maybe of people or in an office where there are people around, the probability that something's skin is some number. Here it's written as omega. So if you give me enough training data, that is, you pay enough undergraduates to circle all the skin areas in an image, or you do Mechanical Turk on Amazon to indicate, to have the world out there for $0.015 a click to say what's skin and what's not skin, you could estimate the prior that any given pixel is skin. So with this training data, I can also estimate that prior, and I can measure those likelihoods, right? Those are the likelihood densities, those histograms that I built. And remember, I need two histograms. I need P of x given skin, what are the hues that I get on the skin, and P of x given not skin. All right, so with that same training data that I use for estimating the prior, I can also estimate my likelihoods. All right, which means I can more or less come up with a rule. Basically, what I'm going to do is I've got my priors, I've got my likelihoods, so I can just evaluate P of x skin given x, and if it's bigger than some number, some theta, okay, I'm going to classify this thing as skin. All right, that's it. Given some new image, I want to label all my pixels. And here's a picture. This is actually a picture of Gary Brodsky. And the thing on the right is showing you the probability of something being skin. And Gary actually was using this to build a perceptual user interface where you could move your head around and the world that you were looking at in some virtual rendering would change as you moved your head. And in fact, here's two more pictures showing you the orientation, right? So here it's pretty much straight up. Here he's turned his head. And all it's doing is tracking the skin pixels of his face. That's all. All right? And in fact, Gary made use of this in a cool little tracker. Remember we talked about mean shift tracking just recently, actually, just a couple lectures ago. Gary did sort of a different version of that called Camshift, which was maybe a little easier to implement sometimes. It's a pretty highly cited paper. And it was basically using these color distributions in order to be able to track your head and change what was rendering. In fact, the picture on here right comes from his paper where they were using the Quake engine for controlling a first-person shooter. And if you just turned your head, okay, the thing would just move with you, okay? And it was just done by tracking the skin pixels.